Okay, let's go ahead and go through the warm-up. I'm going to start up here in the upper left corner. And we'll start with Alfredo. Alfredo, what trig function does that look like? Which parent trig function? Alfredo's vote is for cosine x. Can somebody at that table other than Alfredo tell me why it's cosine x? Natalia, Daniel, why is that cosine? How did we know? We don't know. We'll go to the next table. Gabby, why is that cosine? Very good. We know cosine is the up and down function that folds about the y-axis. It's symmetric. It's even. Very good. Excellent. Next one, number 2. We'll move to the next table. Omar, what is number 2? Omar's vote is for secant. Can somebody other than Omar at Omar's table tell me why that's secant? Alexis or Arlene? Why is that secant? How do we know? Everyone at that table has gone to sleep. Sad face. Aurelie, can you help them out? Why is that secant? Ooh, gotcha. So you see the cosine curve that's connecting those dots? Very good. That's one way to tell. We know secant is 1 over cosine, so it should be related to cosine. The difference between secant and cosecant has to do with whether they have a y-intercept or not, too. Cosecant doesn't have a y-intercept. This guy does. So that's another clue. Very good. All right, Emma. Next one. What is this graph here? That is a tangent. LD, how do you know it's a tangent? Very good. So it's that long S shape, and this guy has a y-intercept. Very good. All right, next one. Juliana, what's this guy? That's a cosecant. Cosecant x. Melissa, can you tell me why it's a cosecant? Very good. It looks like the secant graph, but it's shifted. It doesn't sit on the y-axis. That's excellent. Very good. Next one. If I can count today. Brittany, what is number 5? What is this middle guy at the bottom? You think it's cotangent. How can you tell? So you matched it to the shapes yesterday. And what did we notice yesterday about cotangent? Looks kind of similar to tangent. Does it have the same intercept that that guy does? No. The other thing we can tell, other than that missing 0 intercept, is tangent is usually increasing, cotangent is decreasing. Good. Very good. Last one. Liliana, what is this last guy? This guy is sine. How do we know it's sine? Very good. Sine starts at 0. So sine and cos are the waves. Sine starts at 0, cos starts at 1. Very good. Secant and cosecant are the u's. Tangent and cotangent are those long s's. Good. Very good. So one of the most important skills in this unit is, can I identify those shapes on site? Even if I can't write an equation and I can't graph them by hand, can I at least identify them when I'm looking at them? Very good. Yay. Okay, so let's go ahead and go back to our plan for today. So today we're going to continue working on your notes from last time. So you do need the notes from Tuesday out. I'm going to add another page to it. We're not going to finish it today, and that's okay, because we are covering a lot of big ideas in 6.2. There's 4 functions. They're all kind of complicated. So we're going to introduce some big ideas today on block, and then Friday and all of next week, all we're going to do is practice with those ideas. I don't want to start 6.3 until we're solid on the graphing. So next week is just graphing practice until you can graph in your sleep. Yeah? Okay. Do I have a volunteer who's willing to pass out the 6.2 notes, page 2? Thank you, Vonnie. You guys are going to have to remind me where we left off, because I think you guys are a little out of sync with my second period. I think we were here. Yes. I did. Do you need them? Yeah. All right. So if I remember correctly, while Vonnie's coming around with notes, we left off on the front side of the first page I passed out yesterday. And I got to here and I said, we'll talk about it when we get back to class. So yesterday I gave you about 5 minutes of time at the end of class to start thinking about these. And now we're going to share our answers. And then we're going to look at transformations on those basic shapes. Yeah? Okay. So I'm going to group your comments into 2 categories: similar, how are they similar, and different. How are the 2 curves different? And we're going to start with tangent and cotangent. That was the first one, tangent and cotangent. So how are tangent and cotangent similar? Volunteer, how are tangent and cotangent similar? What do we see? Melissa? Yeah, very good. They have that same basic S shape. Yeah. Right, we know tangent is the increasing S. We know cotangent is the decreasing S, but it's that same basic drawn out shape. Yeah, very good. What else? They're up and down. They have the same range. Yeah. Very good. Their vertical aspects look the same. Words are hard. They both go from negative infinity to positive infinity, all the way up. They have at least one more thing in common. Same period. Good. These guys have a period that's half as long as all the others. They both have the same period of pi. Yeah. Good. What's different about these guys? Opposite domains? Oh, they have different asymptotes. Their asymptotes are in opposite spots. Yeah. If I knew how to spell asymptote, that is. One has asymptotes on whole numbers of pi. One has asymptotes at half numbers of pi. Yeah, very good. What else? Mm-hmm. Yep. Tan goes up, cotan goes down. Yeah. Tangent is increasing, cotangent is decreasing. Yeah, very good. If I were to look at those 2 graphs and I wanted to get from one to the other, I'd have to do 2 things. I'd have to flip it upside down, and then I'd have to shift it because they have different asymptotes. They're connected, they are very similar, but one is flipped and shifted relative to the other. Yeah. That's a little different than what we saw with sine and cosine, where I could pick up cosine and move it sideways and end up with sine. I didn't have to flip it. Tangent, you have to flip and slide to get to its buddy. Okay, next one, secant and cosecant. This half of the room this time. That half's on fire. This half of the room. What's similar about secant and cosecant? What do we see? Very good, Natalia. Yeah, they have the same period of 2 pi. Just like the sine and cosine that they depend on. Very good. What else? They have the what? Very good. No x-intercepts. Yeah. The parent graphs should never touch the axis. If we have a plus d at the end that shifts things up and down, then we might pick them up. But the parent function should never touch. Very good. Anything else? I heard a mumble. Yeah, these guys definitely have the same shape. A full cycle for these guys has one upward U and one downward U for a full cycle. Yeah. What's different about secant and cosecant graphs? Ooh. Yeah. So secant has y int, cosecant does not. Yeah. What else? Anything else? Are there asymptotes in the same spot? I see Paul shaking his head no. Secant and cosecant have that same half pi shift that tangent and cotangent do. So one of them has asymptotes on whole numbers of pi. One of them has asymptotes on half numbers of pi. Half, 1.5, 2.5, 3.5. Much like the sine and cosine that these guys are directly related to, one is just a shift of the other one. So secant and cosecant have a very similar relationship to sine and cosine because they're just the inverses of those. Tangent and cotangent are kind of off in their own little corner because they have functions on top and bottom, and that makes everything messy. Okay, so what we are going to do today is discuss the transformations that we can do to those parent functions, and we're going to introduce the process to graph them. And it's going to look a little bit different than graphing sines and cosines because we have asymptotes where sine and cosine did not, and we have shapes that are a little bit more complex. So let's talk about what those transformations will look like, and then we'll go ahead and move on to graphing. And I have to remember what I wrote down earlier because I have the memory of a squirrel. Okay. So we should all have this chunk on the back side of that paper. Yeah. And the very first thing I'm going to do is I'm going to label those graphs as even and odd. Oh, I should go back and do that on the original. We should label those as even and odd. Do I not have it? I don't have it. Oh, no. On the front side, you should have a little square. And I believe it was tangent, secant, cosecant, cotangent on the front side. Yeah? We should label those as even and odd. That'll help us. You'll need that for homework before we get to that transformation. In the warm-up, one of you pointed out that one of those graphs folds about the y-axis. Which one is it? Of those 4 graphs, which one folds about the y? Secant. Very good. You have your note page in front of you. If it folds about the y, it's even. That makes sense because we know this is 1 over cos, and cos is even. So its buddy should also be even. The other three are all odd. On your homework, they're going to ask you to simplify some expressions before they ask you to do the transformations. So remember that for even functions, because they reflect about the y-axis, if I plug in a negative x value, I'm going to get the same output as if I plugged in his positive buddy. F of negative 2 is the same as f of 2. F of negative 100 is the same as f of 100. For odd guys, we flip about the origin. So a positive x produces a positive y. A negative x produces a negative y. We flip twice, once about the x or the y and then about the x. So this guy, if I put in a negative x, I'm going to get out the same value for y, but negative. The negative sign comes out in front. So when they're asking you to rewrite a bunch of functions for like the first couple of questions of your homework, that's what they're asking you to do. Use the properties of even and odd. It's like a one-liner. I wasn't trying to be me, I promise. Okay, on to transformations. The upside to this is it's going to feel very similar to sine and cosine. You'll notice that those equations all have the same structure. A times a trig function, bx minus c plus d. Just different trig functions, yeah? Edward? I have Edward in 4th period, not 6th. Sorry. Yeah. So let's start with our vertical stretch. That's the guy that takes him and pulls him this way. We called it amplitude with sine and cosine because if I grab the peak and valley and pull, the peak gets higher. Here there aren't peaks, so it's just a vertical stretch for these guys. But it's that same number in front, A, that's doing the vertical stretch. So for example, for secant, where I have those U shapes, if I stretch, it makes the U a lot sharper. Starts to look more like a V with an itty bitty round at the bottom. If I squish inward, it causes that U to flatten out. So the U is going to look pretty flat at the bottom before it goes up on the sides. Same thing with that S shape for tan and cotan. If I stretch vertically, it makes the S less pronounced. It becomes flatter vertically. If I squish this way, the middle gets squished down. That S is more pronounced. Yeah. All right, next guy, period. We're going to do the same thing we did to period for transformations that we did for sine and cosine. If I want the period for sine or cosine, how do I find it? Period is what? Over b. Yeah, over b. Take the period, divide it by b. We're going to do the same thing here. We're going to divide it by the absolute value of b. The question is, what are we dividing by the absolute value of b? B is the horizontal stretch, yeah? Squishes or pulls this way. Bless you. And we're going to do here what we did for sine and cosine. We divide the original period by b. Sine and cosine had a period of 2 pi, which is why it was 2 pi over b. Tangent does not have a period of 2 pi. What is tangent's period? Pi. So for tangent, I'm taking pi and dividing it by b. For cotangent, I'm taking his original period of pi, dividing by b. So same process. Period for the apparent function divided by b. For secant, cosecant, what's the original period? 2 pi. So that's going to look like sine and cos, 2 pi over b. I will warn you, I will probably mix it up today while we're graphing, because I'll have my mind set on one function and forget that I moved to another. You will have to catch me on this. I messed it up like twice in first period today. Okay, so we've dealt with the up and down stretch and compress. We've dealt with the side to side stretch and compress. Now we're going to talk about the translations. Sideways shift, vertical shift. And this is where it gets gross. So phase shift is going to look the same as it did before. How did we calculate our phase shift before? C over B. Same for these guys. So we're still shifting sideways by C over B. What are we doing vertically? Which one shifts up and down? D. Same here. D is going to shift it up or down by however much D is. Yeah, D, D, D. That looks mostly familiar. Now comes the tricky part, which is what happens to the asymptotes. The problem is the asymptotes get affected twice. They get shifted down the x-axis by the phase shift, and they get separated or squished together by that period. So we have to look at both in order to find our asymptotes. So we're going to cut these in half because this table is separated. Tangent and secant have the same formula for their asymptote. Cosecant and cotangent have the same formula for their asymptote. So tangent and secant are buddies here. Cotangent, cosecant, the two cos are buddies here. So I'm going to scoochie this over a little bit. And this is for asymptotes. So both of these are getting that sideways shift of C over B. So if I want to figure out where my asymptotes are, I start with that shift. They're both going to start with C over B plus. C over B plus. The plus, the thing that comes after the horizontal shift, is the original asymptotes divided by B. Tangent and secant had half pi asymptotes. Pi over 2, 1.5 pi over 2, 3.5 pi over 2. Right? It was going every half. So half, 1/2, 2.5, 3.5, 4.5. I need a way to express that. So we know normally it's pi over 2 times k, where k is an odd number, odd integer. That was the original asymptote. We're now dividing by b. I'm going to pick up a b in the bottom. That's the only change, because b stretches them together or pulls them apart. Yeah. Same thing for the cos. Same thing for cosecant and cotangent. Their original asymptotes were every pi, starting at 0, 0, pi, 2 pi, 3 pi, 4 pi, whole numbers of pi. Same thing here. I'm just going to divide it by b. So the original was pi times k, where k was any integer. Now I'm just dividing it by b. So take the old asymptotes, divide them by b, slap on the phase shift. Yeah. We are going to practice identifying these things first. Then we're going to look at what they look like on a graph. Yeah. So the first step in graphing is I have to be able to pick these out of an equation. So I'm going to do one with you because we have a little bit of practice doing that. And I'm going to have you do one in your small groups. Okay? Are we still awake? A little bit, maybe. All right, so I'm going to scooch it up. For example 1, it says identify the constants A, B, C, and D, then find the period and phase shift. I'm going to add an extra set of directions and asymptotes because I think that's good practice for us. Asymptotes. Find the asymptotes. So we'll start with A. A says y equals 2 cosecant pi x minus pi over 2 minus 1. First, I want A, B, C, and D. I know A is in front. So my A is 2. I know my B is in front of the x. I see a pi in front of the x. That must be my B. I know my C is behind the x and it's being added or subtracted, and that the subtraction's built into the formula. That minus sign stays where it is. It's part of the formula. My C is just pi over 2. And then the last piece, my D, that's the plus or minus that's outside of the trig function. What is my D? -1. Good. This guy gets the sign. Very good. And you can identify it like that on your homework. You don't have to make it like a big old list. Doesn't have to be fancy. Just label it on your equation. And they ask us to find 3 things: period, phase shift, amplitude. Or asymptote. Doesn't have an amplitude. A words get confusing. We'll start with period, P. I know that it's something over B. That something is either a pi or a 2 pi. This is cosecant. Cosecant's original period was what? 2 pi. It's the tan and cotan that get the single pi. Yeah, so this is 2 pi over B. And our B is pi. So 2 pi over pi, which is what? 2. Heck yeah, those guys cancel. That makes me happy. I like nice, pretty whole numbers. Good. Next one. Same idea. We're going to do phase shift. So this is how much I slide side to side. Phase shift is C over B. C is pi over 2. B is pi. Take a minute while I'm adjusting e-hall passes. See if you can figure out what that is. Any guesses? 1/2. Yeah, I agree. Because it would be pi over 2 times the reciprocal of pi, which is 1 over pi. So the pi on top, pi on bottom would cancel. Yeah, good. Very good. So we're picking the whole shape, shifting it back half or forward. That's positive. Forward half a square. So we pick up the things, we shift them forward a square. We know our period. Those asymptotes are now 2 boxes apart. Last thing we want to do is find that formula for asymptotes. Yeah. So looking a little bit higher on that page, we know that tangent and secant have the half pies. Cosecant and cotangent have the whole pies. So this should be C over B plus pi over B times K. Because the original period, or the original asymptotes were at pi K, dividing it by B. So I shift, and then I squish them together or squish them apart, two pieces. We know what C over B is. C over B is 1/2. We just did that one. So 1/2 plus, and then pi over B times K. Pi is, or B rather, is pi, yeah? I'm not losing my mind. And pi divided by pi is 1. So this is just 1/2 plus K. Meaning instead of my asymptotes being half pi, 1.5 pi, 2.5 pi, now it's just 1/2, 1.5, 2.5, 3.5. We've squished it down so that we're counting by ones instead of counting by pies. Okay, I am going to put 5 minutes on the clock. In your small groups, I want you to try the same process with B. Identify the 4 constants, find period, find phase shift, find asymptotes. Yeah? So we start with A. Yeah. Normally A is the number in front. There isn't one, which means it's 1. So A is 1. Yeah. Good. We can do this. We got this. Very good, very good. If you're stuck, talk to your neighbors, yeah? Good. Yeah. Now do the math. Good. Very good, Alexis. Yeah. How's it going? A, B, C, and D. Where do you look for A? Normally in front. If there isn't one, it's just
Okay, so
yeah. It can't be 0 because if I multiplied tan by 0, it would just be, yeah, that's not very interesting.
whoa, this one is negative. You see, your C is negative because it's positive, so and then it flips. So this one's supposed to be confusing. Oh, I just
Almost done. 2 graphs, and then I'll give you some homework time at the end of class. I don't. Do you want to run to the front office and ask for some? Okay. I'll make you an e-hell pass.
like a super smart town that every single kid wanted to do the same thing, but then they realized that everybody sounds the same, and then one kid comes.
Yeah.
I have a question. So for here, I would do it's pi plus pi over 2 times b, and 2 times b is 1/4. So like I do it this way?
So you would. And then what is 2 times of 1/4? It would end up being 2/4, which reduces to
1/2.
1/2. And because it's in the bottom, we're going to multiply by its reciprocal. What's the reciprocal of 1/2?
2/1. 2?
2 pi. Yeah.
So we just
The only thing that's missing is there should be a k next to it. Yeah. And in this case, k is odd, right?
Yeah.
Somewhere, yeah.
Yeah.
So it's not 0, 1, 2. When we actually go to find those asymptotes, it's going to be 1, 3, 5 when we calculate with a k. Yeah. And I'll show you what that looks like in a minute. Good. And then you should simplify.
So it would be b or no?
So what's 2 times a fourth? Just look at the denominator for now. What's 2 times 1/4? 2/4 and reduce 2/4. 2 goes into both. 2 divided by 2 is 1/2. So we have pi divided by 1/2. That's a little bit prettier. And when you divide by a fraction, change it to a multiplication problem with its reciprocal. That'll flip that 1/2 upside down. Very good. I see lots of good work happening. Yay! All right, let me section this so we're not getting confused with the last problem. And I need some volunteers. Who can tell me what my A is? 1. How do we know? Very good. You look in front of the trig function, there's no number there. It can't be 0 because 0 times anything would make it disappear. It has to be 1. Good. Very good. B. What is my B? 1/4, 1/4. Very good. X does not come along for the ride. C is, I know it's a pi/4. Is it plus or minus? Negative. Very good. Positive in the formula, changes sign when you pull it out. -4 pi. And then my D I can see is +2. Yay. Very good. All right, next we're going to find our period. We're going to find our period. Daniel, how do I find my period? Yeah. I got an over b. We're waffling between 2 pi and pi. Pi over b, why pi over b? Why pi and not 2 pi? This whole class, why pi and not 2 pi? Tan and cotans have that shorter pi. Yeah. Tan and cotan had the original period of pi. Good. And we know b, you guys told me, is 1/4. So that becomes 4 pi. I see some people nodding and some people looking at me unhappy. Remember that this becomes this when you divide by a fraction. No. Don't be afraid to write it out if you're not good at working with fractions right now. Yeah. Divide by the fraction, you multiply by its reciprocal. Very good. So period is longer. Period's now 4 pi. And then we want our asymptotes. So I'll start with the part I know. I know all of them have a horizontal shift of c over b plus. And the question, is it pi over b or pi over 2b? So did tangent originally have asymptotes at the halves or at the wholes? You're not sure, check your front page. Where were tangents original asymptotes? The odd, the halves, yeah. So I'm going to get a 2 over 2 here. So this is pi over 2b times k. And here k is odd. Here k was an integer, any number. When it's those whole number pi's, it's just integers. When it's the halves, it has to be the odd numbers. 1/2 pi, 3/2 pi, 5/2 pi. Yeah, good. And then we just slap some numbers in that bad boy. So we know C over B. We just found, did we find it? We didn't find C over B. Oh, I guess we're going to do it now. So C over B, this is our phase shift. Yeah. You know, laughing at me and not pointing it out. How rude. C is, what is C? C is negative pi over 4. B is 1 over 4. And then this over here, I'll plug in. I've got pi, 2, and B is 1/4 times k. The question is, what does that reduce to? So C over B, what happens to those 1/4 on top and bottom? Yeah. If I've got 1/4 on top and 1/4 on bottom, those pieces are going to cancel, which just leaves me with negative pi over 1, which is negative pi. So our phase shift is 1 pi backwards. Yeah, this is our phase shift. Yay. The other piece also simplifies. So we're going to do some mental math. Bear with me. I'm going to ignore the numerator. I'm just looking at the bottom. I've got 2 times 1/4, which is 2 over 4. What does 2 over 4 reduce to? 1/2, 1 over 2, yeah. And I know if I have a fraction on bottom, 1/2, that's the same as multiplying by its reciprocal. What is the reciprocal of 1/2? 2 over 1. This is going to be 2 pi times k. Yeah. And k is odd. So when I start figuring out where my asymptotes are, 1, 3, 5, I can't use 0. I can't use 2. K is only odd numbers. Yeah. The first couple steps of our graphing method are just that. Before you ever touch your graph, you're doing that off to the side of the graph, because that's going to help us plot our transformed function. We know what the shapes look like. Now we just got to shift them around. Yeah. So I'm going to do one with you where we'll go over the step list. We'll do a second one together, and then I'll give you some homework time today, and we'll come back and do some more graphing practice on Friday. Okay? Okay. Deep breath. It's going to be okay. So let's graph the function. Graph the function. 1/2 secant x over 2 plus pi over 4 plus 2. And we want to list the steps we're using to construct the graph. What's the very first thing we do? We identify the shifts, right? We identify A, B, C, and D. If I don't know those, I can't do anything. What are the numbers that determine the shifts? A, B, C, and D. So let's do that. For the function in our example, Lonnie, what is my A? 1/2. I agree. Instinct is good. Very good. A is the number in front of the trig function. Sam, what's my B? One over two. Yeah, good. We know it's here, but the x doesn't come along for the ride. Good. B is 1/2. Perfect. Juliana, what is my C? Pi over 4. Positive or negative? Negative. Good. Flip sign. Flip sign. Good. And then my last one, Arlene, what's my D? It's 2. Yeah, the one I haven't circled yet. Good. Good, good. Yay. First step done. Everyone should be able to do that today. Yeah. Identify the 4 numbers. Identify the 4 numbers. Next step, once we know what those 4 numbers are, what did we do with those numbers? Period? Yeah. Find period. What else did we find? Phase shift. And third thing we found, asymptotes. Where are those asymptotes? Those are the things we have formulas for that use A, B, C, and D. Yeah, very good. So let's do that. I'm going to scooch you sideways because I write big. So we're going to do 3 calculations. They ask us for, come on, period. They ask me for phase shift. They ask me for asymptotes. I like to be organized. I know I'm going to be doing the same calculation set over and over again. Yeah. We start with period. How do we calculate period? Something over b, and I heard a 2 pi over b. Why 2 pi? Because it's a secant or a cosecant. Yeah. It's only tan and cotan that have the shorter period. Good. So we plug in our b. Our b is 1/2. So 2 pi over 1/2. And I heard somebody mouth 4 pi. I agree. Multiply by the reciprocal of 1/2, you end up with 2 pi times 2, which is 4 pi. Yeah. Good. Next is the phase shift. Phase shift is C over B. Our C is negative pi over 4. Our B is 1/2. So we turn that into a multiplication problem. So numerator comes down, negative pi over 4, and I multiply it by the reciprocal of the denominator, which is what? 2 over 1. Perfect. And I see some canceling that can happen. 2 and 4 are both divisible by 2. I'm pretty sure that's going to become 1 and 2. So on top, I've got negative pi times 1, which is just negative pi. On bottom, 2 times 1, which is just 2. My phase shift is 1/2 a pi backwards. I'm going to pick up the whole graph. I'm going to shift it by 1/2 pi backwards. Good. Yay. And then the asymptotes. So I know my asymptote formula is phase shift plus, and then it's pi over either b or 2b times k. Need to figure out, is this the 1/2 pi group or the whole pi group? Secant? Secant is half pi. Tangent and secant are half pi. The cos are the whole pi. So this picks up a half pi. So this is 2b, and k is odd for the half pi's. Yes, that is a lot to remember. I don't have it memorized, and I've been doing this for 30 years. That's why you get note pages for your test, right? So don't have it memorized, but have this on your notes so you have it to look at, yeah? And we plug numbers in. We know how to do that. We just figured out c over b is negative pi over 2. Save ourselves some headache. Plus, and then we're going to do pi over 2b. What is my b? 1/2. 2 times 1/2, which is 1, yeah. So I think this is just minus pi over 2 plus pi times k, where k is odd. So negative pi over 2 plus 1 pi plus 3 pi plus 5 pi. In a minute, that's going to make sense. That should connect back to our period, and we'll see that when we graph it. We have done all the legwork. We now have enough information to start plotting stuff. And my recommendation is don't start with the curve, start with the boundaries to the curve. My next step when graphing is to graph the midline and the asymptotes. I know where those are, and I know that those two things determine the shape of my graph. So we start with the midline. Our midline is related to D. D was 2. So my midline should be through 2. I don't have an axis up here. Let's put an axis on here. Y and X. Yours doesn't have to be in exactly the same spot, but we need a coordinate axis before we can shift stuff. So on Y, I'm going to count by ones because that makes sense. On the x-axis, based on my phase shift, it makes sense to me to count by pi over 2 instead of by ones or by pi's. So on the y-axis, I'm counting by ones. On the x-axis, I'm going to count by pi over 2. And I'm going to write that beneath my graph so I remember. Now we can start plotting stuff. So midline is at 2. Very first line I draw, I should have a midline here. Yeah. That's the center of my shape. That cuts the graph in half. And then I need to figure out where my asymptotes are. So I'm going to shift back this way. Our asymptotes are negative pi over 2 plus odd multiples of pi. Yuck. So let's do the first two calculations, and then we can figure out where the rest are. So I need odd numbers of k. K could be 1. What else could k be? 3. Could be 5. Could be 7. But let's do 1 and 3. So if k is 1, I have an asymptote at minus pi over 2 plus pi times 1 is pi. What is minus pi over 2 plus pi? Positive pi over 2, yeah. So my first asymptote should be at pi over 2. Yeah. Then we do it for k is 3. Same process, minus pi over 2 plus 3 pi. So 3 pi minus half a pi puts me where? 3 minus a half? 2.5, yeah. We don't have to be nitpicky. We can just write 2.5 pi. That's totally fine. Yeah, 2.5 pi. Perfect. If you want that in fraction notation, by the way, that is 5 pi over 2. Because half of 5 is 2.5. Yeah. Let's slap those up there. Pi over 2, 5 pi over 2, yeah? So I'm going to shift my graph back down. Pi over 2, that's what I'm counting by. So positive pi over 2 is 1 spot over from the y-axis. That's my pi over 2 grid line. One spot sideways, because each box is half a pi. So that's pi over 2. Next one is 5 pi over 2. So 1 pi over 2, 2 pi, 3 pi, 4 pi, 5 pi over 2. And on my graph, it looks like those asymptotes are 4 boxes apart, which means the rest of my asymptotes should be 4 boxes apart. Every 4 boxes, I'm going to have another asymptote. So I can just start plotting them. Because once I know where the 2 are relative to each other, I know where all the others are. 1, 2, 3, 4. 1, 2, 3, 4. Here is my origin. That's 0, if that helps. Midline is 2 above the origin. I have 1 asymptote, 1 box in front. The asymptotes are 4 apart. Before we do the last part of the graphing, which is actually going way back to middle school technique, we're going to check that this asymptote placement makes sense, because this is the first time you've seen it. So I want to make sure we're making that connection. Secant is an up U and a down U for a full cycle. Yeah. So I need the up U and the down U. That's 2 chunks of asymptotes. Here would be my up, here would be my down. So I want to know how far apart that asymptote and this asymptote are. I'm going to count. Each box is half a pi. So half, 1, half, 2, half, 3, half, 4. That distance there is 4 pi. What is our period? 4 pi. So those asymptotes are matching with what we knew our period would be. If that doesn't check out, we did something wrong in our calculations somewhere. Those asymptotes should match with the period that you calculated. And you know what the shape of a secant graph looks like, so you know how many asymptotes make up a full cycle. This is a good stage to pause and check that your asymptotes are doing what you think they should be doing. Because getting the asymptote right is the hardest part of this graphing. The midline, I know you know how to do. You know how to shift up and down. I've watched you do it. You guys can do that. I know you know what the shapes of these graphs look like. It's those asymptotes that are the butt kicker. So this is a point in the process where you want to pause and check. If I draw my shape in those asymptotes, does the width of that give me the appropriate period for the shape? In this case, yes, it gives us 4 pi. That's not a precise drawing of secant. As a math major, that makes me unhappy. So I'm going to erase that marking. And we're going to go to the very last step of our graph, which is how do I get actual points on a secant curve? And the answer is we go back to middle school. The first graphing tool you ever used. What did you do? Even before a calculator. Yeah, you make a table, X and Y. Y equals blah, blah, blah. We have a formula for Y. Yeah. So that last step is make a table and find 3 points. Make a table and find 3 points. Those 3 points give us an idea of what our shape is. My recommendation is of those 3 points, the middle point should be right smack in between 2 asymptotes. What does the middle of that section look like? I'm going to model that for this graph. Yeah? So I'm going to make my table down here so you can see it. X and Y. We know Y is that ugly secant formula that we're going to plug into our calculator. Yeah. And I'm going to look in one section of the graph. So I'm going to focus on the section of graph between this asymptote and this asymptote. I want to look in here. And in between there, I see 3 points. If I go back one step, I'm at 0. If I go back another step, I'm at minus pi over 2. I go back another step, I'm at minus pi. Those 3 x values are the 3 that are in the middle of that asymptote range. So they're going to tell me what the middle of my graph looks like. And you're going to grab a calculator. And you're going to calculate, and it's going to spit out a decimal, and that's what we want. So grab your calculator. And you're using that function with x is 0. That function with x is minus pi over 2. I'm going to give you like 3 minutes in your small group. Fill out those y values. Yeah? Round it to 1 decimal place past the decimal, because our graph is not super fine detail here.